Okay, so we are in integrated 3 and we are learning 4.4, which is are you rational? And we're doing problems 4 through 7 in Ready, Set, Go. Okay, so it says find the roots and domain for each function. And if you notice 2 and 4 are related, so in reality, I'm going to be doing 2. I'm going to write that down. We're going to be doing 2, 4, and 7, just because in order to do, it's basically the same thing. So let's go ahead and start. So it says find the roots and domain for each function. So the first thing you want to do is the reason why I'm pulling number 2 is because the denominator is this function. So the first thing that I do is I factor this. And if you haven't like learned how to factor, I definitely go back and watch some of those factoring videos just because it's easier. I'm not going to show you how to factor here. I'm just going to do it in my head because at this point, you should be able to look at this and be like, what 2 numbers multiply to get 6, but add to get to 7, and you would say, oh, that's x plus 6, x plus 1. And then they said to find the roots. Roots mean when the whole thing is equal to 0. Okay, so then we're going to basically use the zero product property, which says something times something equals to 0. That must mean one of these or both of these somethings are 0. So I put x plus 6 equals to 0 and x plus 1 equals to 0. So x equals to -6 and -1. So that's the roots for this function. Those are my roots for this function. So when I'm looking at the domain for this function, the domain is, I mean, this is a parabola, right? And so whenever you're looking at domain, things that you should be looking for are denominators. Anytime that you say you can't have something, right? Like, remember how we say we can't have a 0 in the denominator? That tells me that there's a domain restriction. Some people say, well, you can't graph a negative square root, and that's the square root of a negative number, rather. And that is another domain restriction. There's other domain restrictions that we'll talk about, but we've talked about a couple of them already in this class. So think about anything that you can't put into a function. So here we can't put zeros in the denominator, we can't put negatives under a square root, and we can't take the log of a negative number. Those are the 3 that we've talked about in our class. So in this case, I don't have a denominator, I don't have square roots, I don't have a log. So therefore, the domain for this guy is just going to be all real numbers. And it's all real numbers because there's no number that I can't put in here that it would give me some kind of error message on Desmos or a calculator, right? That's not the case down here. So for number 4, it says to find the roots and the domain for the function. Finding the roots for this, I'll show you a couple different ways how to do it. Basically, you're going to set the whole thing equal to 0 and see if that works. Okay. Already right now, you should be like, I don't think that's going to work, Miss Johnson, because this 1 is the numerator on top. And in order for something to be equal to 0 as a fraction, the numerator has to be equal to 0. Well, 1 never equals to 0. 1 equals 1. So, Ms. Johnson, I think the roots for this one, they're not going to have any roots. And we can verify that with the calculator in a second. Okay. But right now, I want to go after the domain. So the domain for this function is going to be all the numbers except for when the denominator equals to 0. So we've already done the work of the denominator equals to 0. It's this. So my domain for this one is going to be all real numbers except -6 and -1. So what's weird here is that we're saying we can't have x being -6 and -1 for this one. And here we say x is equal to -6 and -1 for our roots. And that's because our roots mean when it's equal to 0. And our domain restrictions is when our denominator equals to 0. Do you see how those two kind of like play together or mean each other? Does that make sense? So yes. So now we're going to talk about our roots. I already told you that my thinking on why this has no roots, because in order for it to equal to 0, that's what a root is. The whole thing is going to equal to 0, right? The numerator will never equal to 0. Therefore, this fraction will never equal to 0. So what does that look like in our on Desmos? So let's look at that. So you should have an asymptote. I'm proposing, I think there's an asymptote at 0. I think there's an asymptote at 0. And then, so therefore I am right. You guys all see there is never a time where it's equal to 0, right? Even though this looks like it's going to hit 0, you guys all know what asymptotes look like now. So this one has no roots. This one has no roots. And then write yourself a note. Like I just talked a bunch about why it has no roots. Pause the video and explain to yourself, write a good sentence on why this is not equal to 0. Like, why doesn't this function have any roots, right? Next question. It says, do the roots of the polynomials in problem 1 and 2, so problem 2, tell you anything about the graph of the reciprocal of the polynomial represented in h of x? So they're asking, did this help you figure out this? And the answer is yes, right? We talked about this a little bit. Because these are the roots here, those are the exact domain restrictions, like x can't be -6, x can't be -1, because if it does equal to -6 and -1, our function is equal to 0, our denominator is equal to 0, and when I say denominator equals to 0, your little red flashes, alarms in your head should be like, that's nope, can't do it, right? Because if I pull up a calculator, right, and actually that should be a good thing. Here, let me show you what happens if we plug in 0 there. So let's copy this, paste this, and let's put -6 and -1 here and see what happens. So here, -6, make sure you use parentheses there, otherwise you're gonna not get the right value because it's not going to pull in that negative. Oh no, it's undefined. That's not a surprise to you. It shouldn't have been a surprise that it was undefined because we already figured that out, right? So that's why that is so. Let's see, do the y-intercepts of the polynomials in problem 1 and 2. So 6, this guy's a 6 right here. Tell you anything about the y-intercepts of the functions of problems 3 and 4. So Ms. Johnson, how did you know that this was a y-intercept of 6? Y-intercept means x is equal to 0. So plug in 0 real quick, 0 plus 0 plus 6. That's how I got it. Does it tell you anything? So let's look at our graph again. Does that 6 tell us anything? Does that 6 tell us anything? So let's see. Let's plug in 0 here. Let's plug in 0. And let's see what we get. So we're going to put 0 squared plus 7 times 0. Oh, that's weird. Well, so that would just be 1/6. Wait, Ms. Johnson, that makes sense, right? Because if I plug in 0, 0, I get 1/6. Oh, that makes sense, right? Huh, I never thought about it like that. That's what your brain should be thinking, like, oh, that does make sense. So they're trying to make you put connections together so that your brain makes sense of them, right? So again, the y-intercept here, if you reciprocal that was your y-intercept as well down here, 1/6. Which makes sense, right? Because I plugged in 0 both times, right? Okay, so the rational functions are needed because polynomial functions are not closed under division. What does that mean, Ms. Johnson, not closed? So like bunnies, the set of bunnies is closed under reproduction, right? Like, so if I have 2 bunnies reproduce, I get a bunny, right? You guys are like, oh my gosh, she's talking about sex. Yes, this is, we've talked about this before. So closed under division means like a rational function plus a rational function will always give you a rational function, right? So it's closed under addition. But rational functions are not closed under division, meaning a rational divided by a rational isn't always a rational. I'll say that again. A rational divided by a rational isn't always a rational. But some of you are thinking, but Ms. Johnson, sometimes it's a rational. Yes, but it has to always work. Like a bunny plus a bunny always makes bunnies. Always. Like you never get a cat. Like a bunny plus a bunny is a bunny, or more bunnies, whatever. Okay, so a rational function is defined as the ratio of 2 polynomials. That makes sense. Polynomial on the top, polynomial on the bottom. Some of you are like, Ms. Johnson, that's not a polynomial. It technically is. A number is a polynomial, right? But moving on, where q of x can't be equal to 0. We know that the values of x that makes q of x equal to 0 are not in the domain. We just figured this out, right? So any place that makes that denominator equal to 0 is not going to be in the domain. Is it possible for f of x equals to p of x over q of x to equal 0? Is it possible for it to equal to 0? And here the answer was no, right? Because 1 will never equal to 0. So what do you think? What do you think? So the answer, I will fast forward, maybe you pause it and figure it out. I don't know. So the answer is actually yes. Is it possible? So they're asking, is it possible for this function to equal to 0? And the answer is yes. So here's a quick little example. Let's say my numerator was x and my denominator was x plus 5. Is it possible for this polynomial that's going to show up one day, x over x plus 5, to be equal to 0? So if you remember about fractions, the only thing that you need to know about fractions goes like this. The numerator, in order for the fraction to be equal to 0, the numerator has to equal to 0. Sorry, this is taking too long. Oh, there it goes. So as long as the numerator equals to 0, so my question is, when does this equal to 0? Question mark. Right? And the answer is when x equals to 0. Right? So is it possible? Yes, I just found one. Justify your answer. As long as the numerator equals to 0, and it doesn't bother your domain, right? You couldn't do this one. You couldn't do x over 2x plus 2x squared plus x, right? You couldn't do this one because then it would equal to 0 and the domain restriction is 0. So this is not a good example, right? This is not a good example because of your domain restriction, and your answer would make it equal to 0. See how it doesn't bother it? Watch. If you're not sure, Ms. Johnson, what do you mean by bother it? Plug it in. 0 divided by 0 plus 5. Oh, that's 0 divided by 5. If you had $0 between you and your 4 friends, how much money do you get? 0, right? Here you would get an answer of 0 over 0, which you guys should be like, red lights, Ms. Johnson. You told us we can never have 0 in the denominator, right? All right, thank you for listening. Hopefully this makes sense. The biggest thing that you were supposed to understand here is how your roots and your domain is all dependent on either your numerator or your denominator, right? Your root for your polynomial function or your rational function here is always going to depend on your numerator, like we did here. And your domain is going to depend on your denominator, like we did here. Okay, so get those in your head, because the moment that someone says, hey, give me your roots, you should be like, oh, set the whole thing equal to 0. Hey, give me your domain. You should be like, my denominator can't equal to 0. Do you see how those two things sound the same, but really they are completely different? All right, have a great day.